Welcome to This Explainer. Today, we're going to unpack how chemistry evolved from an ancient quest for immortality into the precise, rigorous science of measuring the universe. You might think of chemistry as just a bunch of folks in white coats holding test tubes, but the story of how we learn to manipulate the physical world around us is far deeper, incredibly ancient, and absolutely essential to our everyday lives.
Here's our roadmap for today. We'll start with chemistry's ancient Indian roots, talk about why it matters today, break down the building blocks of matter, and finally, look at how we measure the physical world.
But before we look backward, I want you to consider these words from Nobel laureate Roald Hoffmann. He said, "Chemistry is the science of molecules and their transformations." This is just a brilliant way to set the stage. It reminds us that chemistry isn't just some static list of 100 or so elements on a periodic table. It's the study of the infinite possibilities that pop up when those elements combine, break apart, and change shape. So keep that core idea of continuous, incredible transformation in the back of your mind as we go through this.
Okay, part 1. Chemistry's ancient Indian roots. Let's uncover the earliest scientific pioneers.
We so often think of chemistry as this strictly modern laboratory science, right? Well, let's rewind and shift our perspective to the ancient world, where it was actually known as Rasayanshastra or Rasvidya. Thousands of years before modern chemistry emerged in Europe, ancient texts like the Rig Veda are already documenting incredibly complex chemical processes. We see the tanning of leather and dyeing of cotton being practiced as early as 1000 BCE. Compare that to the 18th century CE, which is when modern chemistry finally took shape in Europe after centuries of alchemical traditions. It's just a staggering gap between early, brilliant application and modern formalization.
And get this, it gets even more remarkable. An ancient philosopher named Acharya Kanda actually conceptualized the fundamental particles of matter, which he called Paramanu, around 2,500 years before John Dalton's famous atomic theory. Born in 600 BCE, Kanda theorized that all matter is an aggregated form of smaller, eternal, and indestructible units. He even argued that these particles could form pairs or triplets through unseen, invisible forces. Does that sound familiar? Because that is literally the core concept of atoms and molecules, theorized millennia ago, without the aid of a single microscope.
And we're not just guessing here. Archaeological sites and ancient texts offer hard proof of this early mastery. Think of the mass production of baked bricks and brilliantly glazed pottery in Mohenjo-daro, or the sophisticated extraction of metals by the great metallurgist Nagarjuna. But perhaps the most mind-blowing example is the Charaka Samhita. This text discussed the extreme reduction of particle sizes into bosmos, which we now know contain actual metallic nanoparticles. They were practicing early nanotechnology. They were actively applying chemistry to medicine, construction, and metallurgy long before the modern era.
Moving on to Section 2, Why Chemistry Matters Today, Solving the World's Most Pressing Problems.
So why does all this matter right now? Well, because this ancient curiosity evolved into a modern powerhouse that directly impacts our daily survival. From life-saving medications to literally protecting our stratosphere, chemistry provides the tangible solutions we desperately need. Chemists isolate and synthesize crucial drugs like cisplatin and Taxol for cancer therapy, and AZT to help AIDS patients. They've tackled massive environmental crises by creating safer alternatives to the CFC refrigerants that were destroying our ozone layer. And looking to the future, chemistry is designing the specific magnetic and electric materials, like optical fibers, that power the entire modern global communication network.
All right, Section 3, the building blocks of matter, classifying the physical world around us.
To manipulate the world as effectively as we just talked about, scientists first need to categorize absolutely everything that has mass and takes up space. Let's start with the physical states of matter, because the behavior of a substance entirely depends on how its particles are arranged. In a solid, particles are held tightly together in an orderly, rigid fashion, giving them a definite volume and shape. In a liquid, the particles are still close, but they have the freedom to flow and move around. This means they keep a definite volume, but take the shape of whatever container you pour them into. And finally, gases. Gas particles spread far apart with fast, chaotic movement, completely and freely occupying whatever space they are given.
Now, if you zoom out to the macroscopic level, you can further classify matter by how well it mixes. On one side, we have homogeneous mixtures. Think of the seamless, invisible blend of sugar completely dissolved in a glass of water, or the very air we breathe. The particles are uniformly distributed, and you can't tell the ingredients apart. On the flip side, we have heterogeneous mixtures, where the composition is not uniform at all. If you mix salt and sugar together, or grains and dirt,
You can physically see the different distinct components, and you can usually separate them just by simple handpicking or filtration.
And when we drill down into pure substances, we find a really stark difference between pure elements and compounds. Elements, like pure sodium or oxygen gas, consist of only one type of atom. Simple enough, right? But when two or more different atoms combine in a fixed ratio, they create a compound. What's absolutely fascinating here is how the properties completely transform. Take water, for instance. It's a compound made of hydrogen, a gas that violently burns with a pop sound, and oxygen, a gas that actively supports combustion. Yet when they combine in a fixed ratio to form water, the resulting compound is a liquid that we literally use to extinguish fires. How wild is that?
Which brings us to Section 4, Measuring the Physical World, speaking the universal language of science.
To truly understand and manipulate all these physical and chemical properties, scientists worldwide need a strict, unified language. Imagine the chaos of having a chemist in India using one system of measurement while a chemist in France uses another. Well, before 1960, the scientific world was split, with some using the English system and others using the metric system. But the International System of Units, abbreviated as SI, brought much-needed mathematical harmony. Established in 1960, it built on a diplomatic treaty signed all the way back in 1875, finally giving the global scientific community one standardized voice.
This new standardized alphabet relies on just 7 fundamental base units. You have the meter for length, the kilogram for mass, the second for time, the Kelvin for temperature, and a few others like the mole for the amount of a substance. The real beauty of this system is that every single other scientific measurement you can possibly think of, like volume, speed, or density, is mathematically derived from just these 7 fundamental base quantities. It's like the DNA of measurement.
Now, while we are on the topic of strict measurement, it's incredibly important to clear up a common misconception that often trips people up: the difference between mass and weight. Your mass is the actual physical amount of matter present in your body. That stays completely constant no matter where you travel in the universe. Weight, however, is the force exerted by gravity on that mass. Because gravity changes depending on where you are, like you'd experience much less gravity on the moon than on Earth, your weight changes too, even though your mass remains exactly the same.
So let's talk about the unique, frankly mind-bending challenges of measuring things in chemistry. Because atoms and molecules are so incredibly tiny, chemists have to deal with absurdly huge numbers. Imagine trying to do basic math, addition, multiplication, division, with the number of molecules found in just 2 tiny grams of hydrogen gas. You'd be dealing with a number that is over 602 sextillion. That's a staggering string of 23 zeros. Trying to write that out for every single calculation is a fast track to a massive headache.
Enter scientific notation. By using this system, chemists shrink that mind-boggling string of zeros into an elegant, workable format: 6.022 times 10 to the power of 23. That little exponent simply tells us how many times to move the decimal point. It resolves a massive logistical nightmare, allowing scientists to effortlessly calculate everything from the mass of a single invisible hydrogen atom to the speed of light, all without ever getting lost in a sea of zeros.
And that brings us to the end of our explainer. I really hope this has shown you that chemistry is a dynamic, ancient, and ongoing quest. We've traveled from ancient Vedic texts and the brilliance of early atomic theories through the life-saving innovations of modern labs, all the way to the precise global language of SI units and scientific notation. Chemistry truly is the ultimate toolkit for shaping reality. So as we continue to master the rules of matter, what invisible building blocks will we manipulate next? Thank you so much for joining me, and keep asking questions.